Now we shall discuss AC in pure inductive circuit. So we have this circuit diagram, schematic representation of AC signal V of t equal to V0 sin omega t. L is the inductor and I of t is the current flowing, and the whole objective of our discussion is to unfold this I of t and understand how power in the inductive circuit goes. Now voltage across inductor is always L into d dt of I of t. It is first time derivative of instantaneous current. And the Kirchhoff's voltage law, VL is equal to V of t. So whatever voltage we have applied V of t will appear across inductor, and the voltage across inductor is governed by this relationship, and this simple Kirchhoff's voltage law applied signal will appear across the component. So L into d dt of I of t is equal to V0 sin omega t. Now just we have to separate variables and integrate, so this first order differential equation can be solved quickly. So integration d I of t is equal to V0 upon L into integration sin omega t dt. So integration dx we write x, so integration di of t is I of t, that is equal to V0 upon L. Integration of sin of omega t is minus cos omega t upon omega. Now this minus sign can be sucked in, and we can write the same expression using a trigonometric identity, sin of omega t minus pi by 2. So here V0 upon omega L, so V0 upon R, omega L is kind of the opposition to the flow of current. So this is called as reactance. As it is offered by inductor, it is called as inductive reactance. So omega L is a new term appearing in the denominator. This term is frequency dependent. L is the value of inductor, it is multiplied by omega. So higher omega will offer higher resistance. So as omega becomes 0, the inductive reactance will also become 0. So here the term omega L in the denominator is kind of inductive reactance. And here you can see that the current in the circuit lags by pi by 2. Here minus pi by 2 is appearing. Omega t is kind of theta. So the current in the circuit is lagging by pi by 2. So here we have conclusions that V instantaneous voltage is V0 sin omega t. Then in the pure inductive circuit, current is I0 sin of omega t minus pi by 2, where I0 is V0 upon omega L, which you can write V0 upon XL, where XL is omega L. Now we shall describe one circle of certain radius that pertains to amplitude of the voltage, and here this arrow indicates the angle described 0 with x-axis. So as this angle rolls up, one complete cycle is described, and for current we can have another circle of little smaller radius. I have preferred because I am considering always current of some lower amplitude value than voltage, for the consideration that the kind of resistance in the circuit is greater than 1 ohms, and it is lagging, current vector is lagging by pi by 2. So here lagging by pi by 2 with voltage is this direction, and this is how it will roll in the entire circuit. Now quickly we are going to go through the animation. That time you will be able to understand how this rolls with time. So here we have voltage like usual formula V0 sin omega t, and here current I0 sin omega t minus pi by 2. So the moment we subtract pi by 2, the graph is shifted like this. So here blue line indicates current, and you can see how it looks. Now power in the circuit, voltage into current, instantaneous voltage into instantaneous current will give rise to the formula of power. And here we have P of t equal to V0 I0 sin omega t into sin of omega t minus pi by 2. So obviously it is multiplication of these two sinusoidal signals with a phase difference of pi by 2, and here in the first half cycle the power in the circuit is on negative side. That power is delivered by the source and it is stored in the inductor in form of magnetic field, and when the magnetic field collapses back in the second quarter of the cycle, so the power is returned back, and here you can see that power fluctuations are with frequency double the frequency of voltage and current. So here number of cycles are being plotted on x-axis for voltage, red is reserved for voltage, blue for current, and green for power. So here we shall go through the animations which rolls in real time, and you can see how the phase difference plays a role. Now lagging pi by 2 circle starts from negative y-axis. Now in this animation we can see the fluctuations of power. The fluctuations of power you can visually see is with double angular frequency than that of the voltage or current. I guess these animations are quite useful in understanding what is going on. Now we can switch to the next circuit, that is pure capacitive circuit. We have only one element, rather component, capacitor, which is connected to the AC signal, and voltage across capacitor is charge divided by capacitance. Naturally, voltage being function of time, the charge in the circuit will be function of time. Simple Kirchhoff's voltage law will render us voltage across capacitor equal to instantaneous voltage, and we shall replace this Vc by Q of t upon C. Students may remember that the charge in the capacitor Q is always directly proportional to the voltage applied, and the constant of proportionality we define capacity. So Q is equal to CV is the basic relation. So V is equal to Q by C. That is, voltage across capacitor is Q of T by C. Now to know current in the circuit, that is the very objective of our discussion, and I of t is equal to the first time derivative of Q of t, and naturally derivative of sin omega t will be cos omega t multiplied by omega. So here we have omega c in multiplication with V0, and this will define the quantity I0. But we shall take a proper step that we want to look at something in the denominator. So we are enforcing this omega c to go into the denominator. So V0 divided by 1 by omega c. So here this quantity 1 by omega c, we shall define the capacitive reactance. Capital X is reserved for reactance, and as it is pure capacitance playing the role, so we define it capacitive reactance. So V0 upon capacitive reactance we define I0, and cos of omega t we can write sin of omega t plus pi by 2. so that we can have a wonderful comparison that voltage and current together in the same form, except that the current is ahead of voltage by pi by 2. So I0 is equal to V0 upon 1 by omega c, where Xc is 1 by omega c. Now, here we have this red circle indicating voltage amplitude, and this arrow makes 0 angle with x-axis, and as theta changes, rather omega t changes, we describe this vector rolling over this circle in anti-clockwise way. And current in the circuit in the similar fashion is ahead by pi by 2, so it will begin from this point, positive y-axis. So we shall see this also through animation. This is the graphical representation of current being ahead by pi by 2 of the voltage in the circuit. Now, power considerations. Again, power is function of rather product of voltage and current is ahead by pi by 2, and it is represented by this. So here the pink line is indicating power, how it rolls in the circuit. It goes little different than it goes in pure inductive circuit. Later on we shall compare that. So here it shows 3 cycles of how voltage rolls, then current rolls, and power rolls in the circuit. So here is a wonderful animation of how current and voltage, instantaneous current and instantaneous value of voltage and current rolls with time. So here you can see that the phase is ahead by pi by 2. And this graph is including fluctuation of power along with voltage and current in pure capacitive circuit. So this gives a little better intimation. Now we shall discuss power in the AC circuits. Obviously, the instantaneous voltage is V0 sine omega t, instantaneous current is I0 sine omega t minus phi. It depends on the condition whether the phase is ahead or lagging, or if some complicated circuit which is combination of capacitor and inductor, that case we have yet not discussed. So in general we consider phi as the phase difference, and power, instantaneous power in the circuit is instantaneous voltage into instantaneous current. Now here we have sine of omega t minus sine of omega t minus phi. We have a trigonometric relation that sine A into sine B is equal to 1 by 2 inside bracket cos of A minus B minus cos of A plus B. We are going to use this trigonometric identity, and I advise the beginners to pick up a piece of paper and pencil and work out this for A equal to omega t and B equal to omega t minus phi. We end up with cos of phi minus cos of 2 omega t minus phi. So here A plus B will be cos of omega t plus cos of omega t minus phi. So here we have a term twice omega t. So earlier I was referring to you the power considering frequency, double the frequency of voltage or say current. So this term is appearing here, and here there are 2 parts. One part is static, which doesn't depend upon time, and another part is time dependent with cosinusoidal function. Now this above equation represents energy in joules in 1 second, and Here 1 by 2 V0 I0 cos of phi is called power factor, and this is a time dependent part. Now the instantaneous power we can represent by 1 by 2 V0 I0 inside bracket cos of phi minus cos of omega twice omega t minus phi. The energy dW dissipated in time dt will be dW is equal to P of t dt. So to find out the energy dissipated, we need to integrate this equation, say for one complete cycle, and then you can find power dissipated in one complete cycle. Now integration dW will be W, and this integration we may say that rolls from 0 to capital W, where capital W represents power dissipated in one complete cycle, and to describe one complete cycle we need time that rolls from 0 to capital T, P of t dt. So here we have first integration is a constant part, so we are left with integration dt, and integration dt will be t, and upper limit minus lower limit will be capital T. So this whole term inside the parenthesis is capital T minus this integration we need to solve. Now integration cos of 2 omega t minus phi dt will be sine of 2 omega t minus phi divided by derivative of this angular part with respect to time. It will be twice omega, derivative of phi will be 0. So we have 1 upon 2 omega common, sine of twice omega t minus phi, which rolls over limits 0 to capital T. Now if you substitute the limits, so here you have to understand that omega is equal to 2 pi upon capital T multiplied by t. So t is cancelled. So here we have something 4 pi minus phi sine of, and then substituting t equal to 0 will be sine of minus phi. So this integration reduces to capital T, and here we have W equal to 1 by 2 V0 I0 sine of phi into capital T, and you can distribute this 2 in the denominator as under root and under root part, and you can have Vrms into Irms into cos of phi. So final equation that we have power, which is work done per unit time. So here instead of unit time we have one complete cycle describing time that we call period of the segment, and power is Vrms Irms into cos of phi. If phi is 0, cos of 0 will be 1, and if phi is plus pi by 2 or minus pi by 2, then cosine of that value will be 0, and no power will be delivered in pure inductive as well as pure capacitive circuit. But if the value is intermediate, then yes, definitely some power factor will be non-zero. Now here we have P of t equal to V of t into I of t, and the work done dW is equal to P of t dt, and performing integration we have integration dW for one complete cycle. W rolls from 0 to capital W, and time rolls from 0 to capital T, and we have this sort of equation 1 by 2 V0 I0 cos of phi into capital T. Now we shall go through the animation here, and the animation part is phase, and it is animated over plus pi by 2 to minus pi by 2. So as one rolls the phase angle, how this graph of power goes, you can see. So I want to again show you that animation, and as from plus pi by 2 it rolls to minus pi by 2, this blue curve, and you can see how the green line indicating the power in the circuit rolls up. Now if you like to see phase or phase difference on x-axis and power on y-axis, here I shall pick up V RMS equal to 1 and I RMS equal to 1. So it will be, power will be simply cos of phi, and cos of phi is being plotted on this axis. Rather, if you select V0 equal to 1 and I0 equal to 1, then it will be 1 by 2. So 1 by 2 cos phi. Here I have tried to show 0.5 means 1 by 2 into cos of phi, and phi rolls from minus pi by 2 to plus pi by 2. So as you go towards pi by 2, there is a difference. The power in the circuit goes on reducing, and at pi by 2 it becomes 0, and this function is symmetric about y-axis.